Today's lesson is over section 7.4, exponential growth and decay. If we remember from section 7.1, we talked about a differential equation in one of our second examples where population was proportional as it grew. And so that was the differential equation of dp divided by dt, which equaled k times p. And one of the only solutions that worked for that differential equation was y equals the constant of c times e to the kt power. Now we'll be using this because it's an exponential growth function. And so for example 1 here, we're going to assume that the growth rate is proportional to the population size. We're going to use this table to help us model a population of the world in the 20th century. We want to find what the relative growth rate is and how well does the model fit the data. Now here we need to pick an initial value, so let's just start with the earliest or the latest year, which is 1900, and the population was 1650 in the millions. So I'm going to set that as my C, or my initial value, C of 0. And so because we're saying that's 0, then that means 1950, a random point on the table, would be 50 years. Now you can use any value to kind of set up your K. I just chose 1950 because it was right in the middle and it seemed like a good place to start. So I plug in 50 into my time, I plug in 2,564 p of 50, and then I solve for k using my exponential growth kind of experience. And so for k, I'm able to find that it is 0.00878. And so I can go back, plug it back in, and I get the following exponential function. Then from there, now I'm able to make a prediction, see if it fits well. So I need to pick one of the values. I picked 1990 to see how well my prediction or my model fits the actual values. So when I plug that in, I get 3,637.85. Now if I look at the actual value that I'm supposed to get, I can see that my actual and my prediction are not really that close. So I would probably need to choose a different value to kind of see if I can get that model closer. But here it doesn't want us to find the perfect, it just wants us to be able to model. Now as I move over to the next slide, there are different formulas that we can use this for in this kind of process. So Newton's law of cooling, radioactive decay, compounding continuously, all have kind of the same exponential functions. And so all the problems will kind of relate to the same idea. Here I have an example of Newton's law of cooling. So a bottle of soda pop at room temperature, 72 degrees Fahrenheit, is placed in a refrigerator where the temperature is 44 degrees Fahrenheit. After half an hour, the soda pop is cooled to 61 degrees Fahrenheit. I want to find out what the temperature is of the soda pop after another half an hour. And then I'd also like to know how long does it take for the soda pop to cool down to 50 degrees Fahrenheit. So in order to do that, I need to use my Newton's law of cooling because that's kind of what they're talking about. So K times Y will be the differential equation. The Y in this case is kind of the difference in the temperatures. So the initial value, which is T, and then the surrounding value of the temperature where the object is placed. So in this case, that would be 44. And so our initial value, when I put it in the room, it's 72 degrees, or put it in the refrigerator, 72 degrees. So that difference, or that initial difference, would be 28. So I can kind of plug that into my, my equation as my initial value. And then here I want to figure out, they give me a piece of information of after half an hour, so 30 minutes, it's 61. So in this model, I need to know what that new difference is, and that would be 17. So instead of 28, it'd be at 17. So I take 61 minus 44 to get that. And so then that's really my y of 30 equals 17. That's why I didn't write it as y of 30 equals 61. So plugging that into my function, I'm able to kind of solve just like I did for example 1 to find that k value. So notice that from 17 divided by 28 equals e to the 30k power, I'm switching it to logarithmic form, which means I'm moving the e base over to make it ln of 17 divided by 28 and then dividing by 30 to get that k value. And then I plug it in. And so if I want to know what the temperature is of the soda pop after another half an hour of being in the fridge, I would need to plug another 30, so on top of the 30 I already have, so it would be 60. Now notice I added 44 because I'm looking at the temperature now, so I can kind of go, so I'm starting with a base value of 44, and above that is everything else. So when I plug in 60, I'm able to get 54.3 degrees Fahrenheit. Because if I got anything lower, it would be below that 44 mark, which wouldn't really make sense for us to be colder than something that actually is. So that's why the 44 is a necessary means, because that's where we're starting, or that's where we're heading to. Kind of like our horizontal asymptote for an exponential function. Letter B wants to know when it's going to be 50 degrees Fahrenheit. So I take my function and set it equal to 50, and then I solve. So I subtract the 44, divide by 28, switch it to logarithmic form, divide by my k coefficient. That gets me 92.6 minutes. So about an hour and a half. Okay, have fun.